There are about 100 what we call elements on the periodic table of the elements. Now, I have the squiggly equal sign because there's not exactly 100 elements. At the time of this, there's about 118 elements that we've discovered, but depending on the day of the week, you might see a little bit more because we're discovering them all the time. But the issue here is that when you get to the heavier elements, they really don't exist in nature, and they're only made in laboratories, and they only exist for very tiny fractions of a second. So all of those heavier elements that are at the very end of the table, they're mostly radioactive. They're not very stable, and they decay immediately. So I don't really even care to talk about the elements at the very end of the table. We're going to talk about the bulk of the table, which is about 100 elements or so. So in your mind, just think that nature is made up more or less of about 100 elements, and they get heavier as you go across and down the periodic table. Now these elements are the exact same thing that we mean when we use the word atom. So from our point of view, we're going to say that the word element is basically equal to atom. So if I tell you I have, hey, check out this atom on the periodic table, or if I say element number 20 on the periodic table, those are the same thing. An atom and an element are the same thing. They're a unique cluster of protons, neutrons, electrons. We're going to talk about the structure of the atom later, but I know that you know that the nucleus has protons and neutrons in it, and surrounding the nucleus is kind of a cloud of orbiting electrons, and it doesn't look like a solar system. It doesn't look like little planets that go around. It's way different than that, but it's a good picture to have in your mind just to remember that the electrons are out there hanging out in a cloud, and the mass, most of the mass of the atom is actually in the nucleus. And the nucleus is also very, very small, clustered right there in the center there. But atom and element are the same thing. And as you add mass to the nucleus, by adding protons, then you change the character of the element, that we have. And so we start moving across the periodic table like this. All right. Now, we already talked about in the last lesson, we'll say it again, that elements or atoms can join together to form what we call molecules. You can have the same element bonding to itself. That can be a molecule, or you can have two different elements bonding together. So let's write down, obviously, some very simple ones that we know about from everyday life, right? The most famous of which is water, which is H2O, 2 atoms of hydrogen and 1 atom of oxygen. Now this is a molecule because a molecule is any two elements or any two atoms that come together to bond. But this is also called a chemical compound. When you see the word compound, it just means a molecule where you have different elements bonded together. So because hydrogen is a different species than oxygen and they're bonded together like a molecule, we can also call it a compound, right? What would be some other examples of that? Well, right next door to H2O is H2O2. So this is 4 atoms bonded together, 2 atoms of hydrogen, 2 atoms of oxygen. They're all bonded together, and this also is a molecule. Why? Because it's multiple atoms bonded together, right? And it's also a compound. Why? Because it's different types or different species of elements there. Compound means that it has 2 different species going on. What would be another example, right? CH4. This is methane. That's a fuel. It's combustible, flammable. It's also a molecule. And it's also a compound. Okay, why is it a molecule? Just because it's multiple atoms bonded together. Why is it a compound? Because the atoms are different. Carbon is different than hydrogen, and because they're different, we can also call it a compound. So you can see most things in nature are compounds because compounds consist of 2 different types of atoms bonded together into a molecule, and most of the time that's what happens here. Now let's go down and give a couple of additional examples. What about the molecule of oxygen, O2? Now, this is just 2 different oxygen atoms bonded together. Now, it is a molecule, right, because it's 2 different atoms bonded together, but it's the exact same species, so it's not a compound. So we don't call it a compound. You wouldn't say the compound O2. You would just call it the O2 molecule, right? What about nitrogen? Can also bond to itself like that. Of course, it's a molecule, but it's not a compound. And the reason is because these are the same exact species here. So as I said, simple everyday situations, water, hydrogen peroxide, you use this to clean cuts and wounds. Methane, a very common, it's either rocket fuel or just a fuel of some kind that's combustible. They're all molecules. In fact, all of these are molecules, because a molecule is a general term that just means anytime you have more than one atom bonded to something else. That makes a molecule, where it can be a free floating unit that floats around like that, bonded. Doesn't matter what it looks like or what it is comprised of, it's a molecule. Now, you can also have a subtype of a molecule called a compound, where the elements are different. But if they're the exact same species, we just don't call it a compound. That's just a definitional thing. It isn't even that important, but we talk about it because you generally need to know the definitions here. But that is this. Now, why do we go into that? Because we're going to talk about solid, liquid, and gas. And now I want you to know that when I'm talking about a solid or a liquid or a gas, I'm basically talking about either a pure element off the periodic table like aluminum. It's not a molecule. It's just some atoms of aluminum in a pile, right? Or lead, or tin, or copper, or whatever. But I could also be talking, and those are all solids, by the way, or I could be talking about carbon dioxide, CO2. I didn't write that down, but that's a molecule. Carbon monoxide, methane, ethane. I can go on and on about different molecules that are bonded together. And all of those molecules and also the elements can either exist in a solid or a liquid or a gas phase. Right? And we'll also talk a little bit about plasma phase as well, but that's not so much chemistry, that's just more for you to understand. We'll talk about that as well. So, what do we know about solids? All right, solids are exactly what you would think they are. They are literally solids at whatever temperature it is you're talking about. But when we talk about solids, what I really want you to know is that they have a definite volume. A definite volume. So think about a sugar cube. A sugar cube is a cube about 1 centimeter on each side, and it is a solid. Of course, I can crush it, but it is a solid at room temperature, right? It's not flowing anywhere. It's not floating off like a gas. It's a solid. If I take that sugar cube and put it into a glass, not a glass of water, but just into an empty glass, what will happen to the sugar cube? Well, it's still going to be a cube. Right? So the properties of a solid are that when you put it into a container, the container has no effect on the size of the solid. So I will say container has no impact on the shape and size of the item that you have. If I have, a giant hunk of copper and I put it in a container, not water, just a regular container, it doesn't do anything. It still has its own shape and size. And we also know, or maybe you don't know, but you'll learn now, that it's incompressible. Incompressible, or not compressible. Right, in general. So if you think about iron, for instance, if you try to squeeze it, what's going on at the molecular level is that all of the atoms are as tightly packed as they can be together, and there really is no room for the atoms to move past each other, because everything is kind of cooled down. Because you think about solids, or when things are cooler, you'll think about ice, right? And they're so cool that they are moving, they're vibrating. Well, everything's vibrating down there at the atomic level, but they can't slip past each other. The atoms can't flow, and that's why solids don't pour, and that's why they have the same shape. They don't take on the size of the container, and they're not compressible. If you squeeze copper, now I say they're not compressible. Of course, you can put it in an industrial press with millions of pounds of force and it'll squeeze it, okay? But in general, you can't really squeeze it very much because the atoms are already as close as they can really be. You might be able to compress it a tiny bit, but in general, we say that solids are not compressible because the atoms are already so close together. So that's a solid, right? What is a liquid in general? Right? What is a liquid? We all know what a liquid is. We drink water every single day. What does it mean? A liquid is when the atoms are very close together, but they're not quite locked into place. They can bounce off each other and slide past each other and then hit the next one and slide past that one. And they're not rigidly locked in place, vibrating like a solid. They can generally move past each other just a little bit so that if I try to pour it, it can flow. That's why liquids can flow, because the atoms are extremely close together, but they're not so close together that they're rigidly held in place. They can still slide past each other a little bit. Of course, if you take that liquid and you cool it down further like water and cool it down and freeze it into ice, then everything slows down and it locks into place into some structure where it's not flowing anymore, and that's why ice is solid and ice doesn't pour. But in the liquid phase, the atoms can very gently move past each other, and so it can flow, right? And liquids, they're kind of, see, we say a solid is not impacted by the container, but a liquid has some impact from the container. Now, what I mean by this is that if I put the same amount of water into this container, it might come up to this level. But if I put the water into something this size, then it's going to be down at this level. So you see the water does sort of expand to fill the width of the container, but not the same way that like a gas does. We'll talk about a gas in a minute. A gas expands to fill the entire container. And a solid, it doesn't have any effect. The container has no effect on a solid. A solid just sits there, you know, as a nugget or something. But a liquid does sort of expand sort of sideways to fill the container, but not in the way that a gas does. So I say that it has some impact from the container, okay? And a liquid also has a definite volume. In other words, if I have a solid, it has a definite volume, the container has no impact at all, and it's not compressible. A liquid has some impact from the container. It does sort of expand sideways to fill the container, but it doesn't fill the volume of the entire container, like this is all empty up here, and it also has a definite volume as well. If you put it into a smaller or a larger container, of course, it changes shape a little bit. It's kind of in the middle there, basically. All right, and then let's talk about, oh, and also, I want to tell you, liquids in general are not compressible. Right? If you take water and you put it into a press and try to squeeze it, you might be able to squeeze it a little bit, but it's not going to be very compressible at all because the liquid water molecules, again, are extremely close together. They do and they are able to slip past each other very, very kind of like with a small margin. They can just barely, it's like a crowded room, they can barely get past each other, but it's still extremely tight. And I cannot compress it much because there's not much space between the molecules or the atoms. Now let's compare this with the gas, with the gas phase. Now gases have no definite volume. Definite volume. Right? And what do I mean by that? It's sort of like the volume that a gas occupies really just depends on the container. If I have a gas inside of a ball this big, then it's going to fill this entire space of this ball. But if I take that gas and transfer it into a volume this big, then it's just going to expand in order to fill that volume. And if I take it and put it into a volume the size of this room, it's going to expand even further. So the container basically defines the volume of the gas. So it expands to fill the container, expands to fill the container. And what's the big difference? We said solids and liquids are not compressible, gases are compressible. Right? If you take a gas in a container, in a piston, think about a car engine with a piston pushing, and it's squeezing the gas. Now, things are going to happen to that gas. The gas is going to heat up. There's going to be friction there. But you are going to be able to have the ability to compress it. Why? Because in a gas, the atoms are much farther apart. In a gas, the atoms are moving really, really fast, and they're smashing, and they're bouncing off, and they're bouncing off, and they're bouncing off, and they're hitting the walls, and they're hitting the atoms, and they're bouncing and bouncing. And if I compress it, I can reduce the distance between the atoms. Maybe they bounce more often, but I can make them a shorter distance because they're already so far apart. But in a liquid, they're already on top of each other. In a gas, they're locked into place. So solids and liquids are not compressible. Gases are compressible. And of course, a gas expands to fill the container, whereas the solid and the liquid really doesn't. Now, a liquid's sort of in the middle state where it kind of expands sideways to fill the container, but it doesn't really take on the full shape of the container. All right, so now what we want to do is we want to answer a little question just to kind of get some practice with this and make sure we understand. Let's just take a couple of different scenarios. What about helium in a balloon? Helium in a balloon. All right, so the question is, what we want to do is want to ask, are these solids, liquids, or gases, and why? Well, if it's in a balloon, you know that it's basically taking the entire shape of the balloon. You can in fact make the balloon bigger by pumping a little more gas into it and making it expand, right? Or if you just put it into a larger container, the gas would expand to fill the container. So you know that helium has to be a gas because it takes the shape of the container, the balloon shape, and it expands to fill the entire container. So no surprise, helium in a balloon is a gas. And I know that you already knew that, but we want to talk through it to make sure we cover all the bases here. What about mercury in a thermometer? Right? So mercury in a thermometer. A thermometer is a glass tube, and we have something inside of that we're using to measure the temperature. Is it a solid, liquid, or a gas? Well, it has to be a liquid, because if you look at the mercury, it does sort of expand sideways to fill the shape of the container, but it can go up and down as it gets warmer. You know, as your body temperature heats it up, it might rise in the column. If it gets colder, it might go down the column. So it doesn't totally take the shape of the container, but sideways, it does expand sideways to fill that container, and so it's a liquid. So mercury in a thermometer is a liquid. Right? All right, let's take a look at the next one. We only have a couple of these left. What about soup in a bowl? And I know you already know this as well, but of course this is a liquid. Why is that? Because if you have a bowl here, like this, and you have soup in there, then it's going to expand to fill the container kind of sideways, but obviously will not expand to fill the entire container. And we know that it can be poured. We can pour liquids, and we can also pour gases too in a lot of cases. But we know that we can't pour solids, for instance. We can pour this. It takes the sideways shape of the container, and in general, we know that that is what a liquid is. All right, let's do one more, right? And we're going to talk about frozen water, otherwise known as ice. Is that a solid, liquid, or a gas? Well, in frozen water, you know that you can't pour it. If you think about an ice cube, you can't pour it. You know that it's not a gas because it doesn't expand to fill the container, and it can't be poured, so it's not a liquid. It has to be a solid, of course, it's a solid, and that's because the water molecules they're basically locked into place. They don't slip past each other, but they're vibrating there, and as you get it colder and colder, they vibrate less and less, but they really can't move past each other, and so it has a definite volume there. So frozen water, we know, is a solid. Right? Now, I want to close this out by talking a little bit more about the liquid phase, and I also want to talk a little bit more about water in specific. Now, this is just an introductory lesson. It's one of the first lessons in all of our chemistry sequence. But there are some things that are so critically important in chemistry that I want to repeat them several times, so that maybe the first time you hear me, you don't quite understand. Maybe the second time, maybe you'll understand a little more. Maybe by the third or the fourth time, you'll just remember it, and you won't have to like wonder. It'll just be burned into your brain, because some things are so important, I want to burn them in your brain. Okay, so I did mention this in the last lesson, but I want to mention it here because it's that important. So let's talk about the famous H2O molecule, right? The most important molecule in all of life, probably in all of chemistry, right? We know that it's 2 atoms of hydrogen bonded to 1 atom of oxygen. But later on, when we study the structure of water and the structure of molecules, we're going to learn that what this thing really looks like is an oxygen molecule in the center and a oxygen atom in the center here, and 2 hydrogen atoms, 1 on each side, but they're not right on each side. They're kind of slanted down, and this oxygen is bonded to this hydrogen, and this oxygen is bonded to that hydrogen. So sometimes, you see, we write it as H2O, but sometimes you might call it HOH. Sometimes people say that water is HOH, and that's exactly the same thing. It's 2 hydrogens and 1 oxygen, 2 hydrogens and 1 oxygen. Now, why am I writing this? I promise this is going to come right into the idea of gases and liquids and such here in just a second. Just stick with me for a minute. Now, these lines, they represent the bonding that's happening between the hydrogen and oxygen. And we haven't talked about bonding yet, but you just need to know that when you bring things together, sometimes they bond. And that means that there's an attractive force that holds them together, and you could break the bond. Of course, you can rip it apart, either with heat or with something else, some other chemical reaction. But if you don't do anything to it, it's going to stay like this, bonded. And water, if you don't do anything to it, if you don't break the bonds, then they're going to stay bonded like this. Now, what is a bond? and I told you this in the first lesson as well, there are people that study this kind of question for their whole career. And I want you, as you learn all these chemistry topics, to understand that we don't know all the answers. We have a pretty good idea about chemical bonding. We know how to calculate the strength of a bond. We know when bonds happen and when they don't happen. But when you zoom into what electrons really are, it's difficult to visualize exactly what's happening at the chemical bond level because it's all quantum mechanics. Quantum mechanics is a branch of physics and chemistry that deals with extremely small things. So I can draw a picture for you with sticks and letters and tell you what's bonded, but there's really no stick down there between these atoms. It's something else going on causing them to be stuck like that and kind of held in place and bonded. But I guess I just want to tell you that even though I'm going to describe it here, the details, you could actually make an entire career studying how bonding works and how bonding happens because we don't know all the answers, I guess is what I'm trying to say. But what I do know is, and what we all know collectively as science, is that this hydrogen atom, it had an electron with it in the beginning. And this hydrogen atom had an electron with it in the beginning. And this oxygen atom had electrons with it in the beginning as well. And when you bring the hydrogen and the oxygen together, they like to share electrons. And what this line is representing is the electrons being shared between these two atoms here and these two atoms here. And when the electrons get to be shared, we call it a bond. And it has a certain strength to it because the details of which is what you could spend the rest of your life studying, as I'm telling you. But basically, when they come together, it reaches what we call a low energy state. And basically, it becomes energetically favorable for it to stay in that state where the electrons are shared. And it all, again, comes back to what I told you in lesson number 1, the electric force, the force between electrons, or the force between electrons and protons, that electric force is millions and millions of times more strong than gravity, for instance, holding me to this planet. Now, we don't often see that because all of the atoms that we interact with, they all have equal number of protons and electrons, equal and opposite charges. So they kind of cancel out. But if you have a charge imbalance of any kind, then basically the strength of that electric force becomes apparent. And the electric force is literally millions and millions and millions of times stronger than gravity. It's one of the strongest forces in nature. It's way stronger than we give it credit for because we see gravity every day. We think it's strong, but actually gravity is very, very weak compared to electricity, okay? Why am I telling you this? Because this represents a bond, a sharing of electrons. This represents a bond, a sharing of electrons. And you would think that because they're sharing them, the electrons are kind of like shared right in the middle between these two atoms. And these electrons would be shared in the middle, right in between these two atoms. But actually, the oxygen atom is able to pull the electrons just a tiny bit closer to it. It's a little bit stronger of an electron attractor. And why is it a stronger electron attractor? Well, we get into that later, but it's because the electric force is so strong. And oxygen is able, because of its electron setup, it's able to attract electrons a lot stronger. So what happens is, you would think everything would be balanced and the electrons would be right here, but actually oxygen is able to pull the electrons closer. And this oxygen is able to pull the electrons a little closer. And that means that this oxygen atom is not neutral. It has a very slight negative charge. And we write that as a little Greek delta, which looks kind of like a little snake with a little negative sign there. This delta, don't worry about the symbol. It just means that there's a very slight negative charge there because the oxygen pulls them just a little closer to it than from the hydrogen. And because those electrons are pulled a little bit this way, then what is left behind, since they have protons in the nucleus here, you have a very slight positive charge on this hydrogen atom and a very slight positive charge on that hydrogen atom. And that's because the electron that was here, sharing with one of the electrons that was here, you would think they'd be in the middle, but actually they're pulled towards the oxygen because the electric force is so much stronger. It's basically because the oxygen has more protons in the middle, and because protons attract electrons, it's able to pull them a little bit closer to it. And when it does that, it has a slight negative charge on the oxygen. In each of these hydrogen atoms, because there's a proton in the middle, in the nucleus, it has a very slight positive charge left behind. Now, what is this called? This means water is polar. Polar just means that one side of the molecule is negative and the other side of the molecule is positive. Now, you might say, This lesson is all about solids and liquids and gases. Why are you talking about water? And why are you trying to tell me that half of the water molecule is positive and the other half is very slightly negative? Here's the chance to, here's why I want to tell you that, okay? Because this governs this polar nature of water. The fact that it is very slightly positive on one side and negative on the other side. It governs the properties of water in a really important way. We know that water is polar, which just means one half of every water molecule you drink is slightly negative, and the other half of every molecule you drink is slightly positive. And because it's in a liquid phase when you drink it, let's say, the water molecules can slide past each other. Remember, that's what we just talked about. In the liquid phase, they can slide. That's why you can pour it. But if you think about it, if this is one water molecule, if you have a copy of it right here, then you would have a copy of oxygen and hydrogen, and one half of, I'll just draw it right here. Let's just do it. Why not, instead of talking about it? So there's a hydrogen right here and another one right here, but this oxygen is very slightly negative and this hydrogen is very slightly positive and this one's very slightly positive. What's going to happen when these interact? Well, the negative side of the molecule is going to be attracted to the positive side of the other molecule. And this positive side of this molecule is going to be attracted to the negative side of the other molecule. So as the molecules of water slide past each other, if it comes into contact positive to negative of the different molecules, it's going to kind of like get stuck together for a split second and then maybe bounce off and go the other way, right? And likewise, if the negative end bumps into the negative end, it's going to be repelled very strongly and bounce off very strongly. So why am I telling you all this? Because as the polar nature of a molecule increases, goes up, then the boiling point also goes up, right? And that's just something that I want you to know because it's neat and it kind of like it shows you at the molecular level why this is happening. If you think about it, what does boiling mean? It means I add heat to something. And then what ends up happening is the liquids that are flowing past each other, they get enough energy, they start shaking, they get enough energy to escape from the top. But if these molecules are charged on one half than the other, they're sticking to each other a little bit. Every time they bounce into their partner, they're kind of, and then they bounce off and they stick a little bit and they bounce off and they stick a little bit and they bounce off and they stick a little bit and they bounce off. So if you have a liquid with a very highly polar molecule, then it's going to require a lot more heat to make those things fly off into the gas phase. Because every time they bump into their neighbor, they want to stick. Now, the thermal energy, the heat that you're putting in, can overcome that, and eventually they can escape, go to the gas phase and boil. But it's going to take more heat to do that if you have a very highly polar substance. Compare that to a liquid that is not polar at all. And there's plenty of liquids that aren't polar. Then there's no sticking of the molecules. There's no attraction, intermolecular attraction between the molecules. And so they have a lower boiling point because the boiling point is just the temperature required to give the molecules enough energy to escape. But if they're constantly sticking to their neighbors, then they're going to take a lot more energy they're going to need a lot more heat to make them bounce off and escape. And I just wanted to point that out to you because we're talking about solids, liquids, and gases, and talking about gases and filling the container and kind of think about boiling, going from the liquid phase to the gas phase. And something like the structure, the detailed structure in water in this case, can very much govern some of the properties that we see, like the boiling point, right? And so on. So I just wanted to point that out. And the other reason I pointed it out to you is because I want to draw this over and over again. I want you to know that water is polar, which means half of the water molecule is slightly negative, and the other half, the hydrogen ends, are very slightly positive, because that behavior of water is going to come back over and over and over and over again and influence a lot of real life chemistry. I want you to remember it. So every time I have a chance, I'm going to draw it, and you might see it over and over and over again, but that's okay because I want it to sink in. You know, we think of molecules, when you first learn chemistry, you see the pictures in your book and you think molecules are all like neutral or whatever. But I told you now that, and I haven't told you why water is bent, by the way. We're going to learn why it's bent later. That's a story for a different day. But I have told you why half of it's negative. And that's because oxygen is able to pull the electrons that it's being shared very slightly closer. And why is it doing that? It's because the electric force is so incredibly strong. And why do the adjacent water water molecules want to stick to each other? Well, it's because the electric force is so strong, and so on. And if you cool the water, if you take liquid and you cool it down, then they're slowing down, slowing down, slowing down, slowing down. And what's going to happen when you finally get them so slow that they're not really moving past each other very much? What's going to happen? This negative side is going to attract this, and this positive side is going to attract this, and it's going to get locked into a lattice, and that's the crystal lattice of ice. All right? So if you zoom in on a microscope of ice, in a microscopic image of ice, or if you could see the molecules of water of ice, they're all arranged so that the oxygen end is kind of right next to the next door neighbor of the hydrogen end, and here's next door neighbor of this, and they're all arranged into a perfect little lattice where they're all kind of like very close to their neighbors. Why? Because the electric force is so strong. The electric force governs everything from the properties of water, the way water can dissolve things, the boiling point and the melting point of substances, and it governs all kinds of other things in addition to that. So, in this lesson, we covered the idea of what is a solid, what is a liquid, what is a gas. We talked about the properties of them. We did an example problem. And the last thing I'm going to leave you with is the concept, after solid, liquid, gas, comes the concept of plasma. And I save it for the end because it's really not as important for chemistry. But plasma is if you just start with ice, let's say, liquid water, okay, or solid water. Then you put some heat into it. It turns into a liquid, right? You put enough energy into it so that they can escape the attraction between the molecules that are in that lattice we just talked about, and they can start to flow past each other. That's liquid water. Then you put more and more and more heat energy in. Eventually they start moving so fast that they can break their attraction, the intermolecular attraction, and go off as a vapor, a gas water vapor, and now it's gas phase. If you take the gaseous water and you put more and more and more heat into it, you're going to break apart the molecule into hydrogen and oxygen constituents. And then if you put more and more and more heat into that, you're going to break apart the oxygen atom. You're going to take the electrons away from the oxygen. You're going to take the electrons away from the hydrogen. And that's called a plasma. So a plasma is when you take an atom, let's say, any atom, a chlorine, let's say, and there's electrons that are on the outside, and you put so much energy into it that you take the electrons away. So you're left with a charged soup of electrons floating around, and then the atoms are left behind as well, and they don't have as many electrons as they did, so they're charged as well. And this charged soup is what we call a plasma. And that's what's inside of our sun and every star. That's kind of like the fourth state of matter, but it doesn't affect chemistry because that's more of a nuclear thing. Chemistry is dealing with electrons and electron transfer, so we don't usually talk too much about plasma. I just wanted to bring it up because, you know, it's neat and I just want you to have a complete picture. So, watch this lesson a few times if you need to understand the difference between solid, liquid, and gas. Remember, water is polar, which means half of it has a slight negative charge, the other half has a slight positive charge. And remember, most importantly, that everything in chemistry, almost everything in chemistry, is governed by the fact that electric force between electrons, or electrons and protons, is millions and millions and millions of times stronger than gravity. So it is extremely strong and governs pretty much all of chemistry at the basic level. And we're going to talk about that as we move on. So watch this, make sure you understand this lesson, follow me on. Till the next lesson, we will continue to build your skills in chemistry. Learn anything at mathandscience.com.